When we started this investigation, the question seemed simple. Why do some nuclear projects finish years earlier than others? But the evidence forced us to change that question, because construction time isn't explained by a single country or a single decision. It's the result of an entire system. And that leaves us with an even more difficult question. What inside that system actually causes delay? Every major nuclear project leaves behind thousands of pages of reports, construction records, schedules, engineering assessments. Somewhere inside those documents, the evidence is waiting. There are many explanations: politics, regulation, reactor design, supply chains, financing, workforce. Some of them may be true. Some may explain only part of the story, and some may not survive the evidence at all. That's how complex engineering problems are investigated. Not by defending assumptions, but by testing them. So in this investigation, we're going to do exactly that. We'll take each explanation, treat it as a hypothesis, and ask a simple question. Does the evidence support it? Hypothesis 1. People often speak about nuclear construction delays with remarkable confidence. It's regulation, it's politics, it's financing, it's the reactor design, it's the supply chain, it's the workforce. Everyone seems to have an explanation. The problem is that a convincing explanation isn't necessarily a correct one. Large engineering projects are rarely explained by a single cause. They're the result of many systems interacting with one another. Sometimes one system becomes the bottleneck. Sometimes several problems appear at the same time. And sometimes one small issue creates a chain reaction that affects everything else. So before accepting any explanation, we'll treat every one of them the same way. Not as conclusions, not as opinions, as hypotheses. A hypothesis isn't something we believe, it's something we test. And that's exactly what we're going to do over the next chapters. We'll examine each of these hypotheses against evidence from real nuclear construction projects, official databases, OECD analyses, IAEA records, and industry reports. Some hypotheses may explain part of the story, some may prove surprisingly important, and some may not survive the evidence at all. Because complex engineering problems are not solved by choosing the explanation we prefer. Every explanation deserves the same question. Does the evidence support it? One of the most common explanations for nuclear project delays is regulation. And at first glance, it sounds almost self-evident. Nuclear power plants are subject to some of the most stringent safety frameworks in any engineering industry. Every system must be reviewed, every component must be verified, every step must be documented. So the argument seems simple: more regulation, more delay. But in engineering, simple explanations are rarely complete explanations. So instead of accepting this as a conclusion, we turn it into a hypothesis. If regulation is the primary driver of construction delays, we should expect a consistent pattern. Projects operating under similar regulatory regimes should show similar construction timelines. But when we look at real-world construction data, that pattern is not consistent. Some projects with equally strict safety requirements still show very different construction durations. This suggests something important. Regulation is not irrelevant. In fact, it is essential for nuclear safety. But its role in construction delay is not straightforward. It does not act alone. It interacts with other systems: design maturity, supply chains, project experience, and execution capability. So at this stage, we can say the hypothesis is only partially supported. Regulation influences nuclear construction, but it does not, by itself, explain the large differences we observe between projects. And that leads us to the next question. If regulation is not the dominant factor, what about financing? After regulation, the next most common explanation is financing. Nuclear power plants are expensive, extremely expensive, billions of dollars, long construction timelines, high upfront capital costs. So the argument seems straightforward. If a project is delayed, it must be because the financing is difficult. At first glance, this hypothesis also feels intuitive. Large infrastructure requires large investment, and large investment introduces risk. Risk leads to caution, and caution can slow down execution. But again, intuition is not evidence, so we treat financing as a hypothesis, not an assumption. If financing were the dominant factor, we would expect a clear pattern. Projects with similar funding structures should show similar construction timelines, and projects with stronger financial backing should consistently perform better. But when we look at real nuclear construction history, the picture is more complex. Some heavily state-backed projects still experienced long delays, while some projects with different financial structures performed comparatively better than expected. This suggests something important. Financing is not irrelevant. In fact, it is critical to whether a project starts at all. But once construction begins, financing alone does not fully explain the variation in delay. So at this stage, we refine the hypothesis. Financing influences nuclear projects strongly, but primarily at the decision and initiation phase, not as a standalone explanation for construction delays. And now the investigation continues. If regulation and financing are not sufficient explanations, then we need to look deeper into the engineering itself. The next hypothesis is more technical. Reactor design. After regulation and financing, there is another explanation that often comes up. Reactor design. The argument is simple. If a reactor is complex, it will take longer to build. And again, this sounds reasonable. Different reactor types have different architectures, different safety systems, different levels of standardization, different construction methods. So the hypothesis is more complex design, longer construction time. But in engineering, complexity alone is not enough to explain outcomes. So we formalize it. If design were the dominant factor, we would expect a clear pattern. Standardized designs should consistently perform better. New or first-of-a-kind designs should consistently perform worse. And projects using the same reactor design should show similar construction timelines. But when we look at real construction history, the evidence is more nuanced. Projects using similar reactor designs can still have significantly different construction durations, and in some cases, even standardized designs experience major delays. This suggests something important. Reactor design influences construction complexity, but it does not operate in isolation. One key insight emerges here. Design is not just a static input, it evolves during construction. Changes in design can trigger rework. Rework can impact schedules, and schedule pressure can introduce further inefficiencies. So at this stage, we refine the hypothesis again. Reactor design is a major factor in construction complexity, but its impact on delay is strongly dependent on how stable the design is during construction and how mature the design is before construction begins. And this leads us to a more subtle question. If regulation, financing, and design are not sufficient on their own, then what happens when all of them interact together? The answer may lie in something less visible, but far more powerful: the construction system itself. By this point, we have tested several common explanations: regulation, financing, reactor design. Individually, none of them fully explains the variation we see in nuclear construction timelines. But something important has emerged. Each of these factors does have an effect, just not in isolation. In complex engineering projects, the outcome is rarely determined by a single variable. Instead, it emerges from interactions. A delay in one area can propagate through the entire system. Design changes can affect procurement. Procurement delays can affect construction sequencing. Construction delays can force regulatory reevaluation, and regulatory feedback can trigger further design adjustments. This creates something important: a system where small inefficiencies do not remain small. They accumulate, they interact, they amplify each other. So the question shifts again. It is no longer what causes nuclear project delays, because that question assumes a single cause exists. Instead, the more accurate question becomes, what conditions lead to predictable nuclear construction performance? At this level of analysis, individual hypotheses become less important than the structure connecting them. Regulation matters, financing matters, design matters, supply chains matter, experience matters. But what determines the final outcome is how these elements interact over time. So rather than identifying a single cause, we begin to see a pattern. Successful nuclear construction projects tend to share certain systemic properties: less volatility in design, more standardized supply chains, stable financing structures, consistent regulatory environments, and accumulated construction experience. Which brings us to the conclusion of this investigation. Not a single answer, but a framework, because in nuclear construction, performance is not defined by individual factors. It is defined by system coherence. And once you see that, you cannot unsee it. This is Reactor Atlas, exploring nuclear energy through physics, not fear.